Hi guys, welcome to another video where we take a look at another interesting problem from mathematics, where we can have a look at the problem solving process, how it works, what it looks like when it comes to finding the solutions to non-routine problems in mathematics. So the problem that I've got for this video is from the book Vector Calculus. This is the 5th edition. And the authors are Marsden and Tromber. So we're looking at page 89 in this book, and it's problem number 10. So I've got my notes just to hand here, just to refer to when I need to. So I'll describe the problem first, state the problem, and then there's a few things that I just want to say about this problem before we get stuck into it. So the problem is, show that three vectors A, B, C lie in the same plane through the origin if and only if there are three scalars, alpha, beta, gamma, not all zero, such that alpha times A plus beta times B plus gamma times C is equal to 0. So what we have then are the vectors A, B, C, and these lie in the same plane through the origin, and that's going to be important, through the origin, if and only if there are constants alpha, beta, and gamma, such that not all zero, such that alpha times A plus beta times B plus gamma times C is equal to 0. And just to clarify, that's the 0 vector. Hopefully, throughout this video, I will remember to underline my vectors. If I don't, then I don't. It's as simple as that. Okay, so I've not missed anything, have I? Okay, right. So, for those of you that know about vector spaces and things like that, this will be a very, very straightforward problem, because as we can see, if the plane that we're interested in is a plane through the origin, and that makes it a vector space, in particular a two-dimensional vector space. So if it's a two-dimensional vector space, that means that any two linearly independent vectors in that plane will suffice to form a basis, and then such that any third vector can be written as a linear combination of those two basis vectors. So let's say that A and B are linearly independent, which means in this context that they're not constant multiples of each other, and that would mean then that the vector C could be written as alpha times A plus beta times B equals C. So if we took gamma to be equal to -1, then we've proved the theorem, and this would be an if and only if kind of theorem as well. We'd be proving it in both directions. So that's how things would look if we look at things through the lens of linear algebra and using finite dimensional vector space theory. If we look at things from that perspective, it's easy. You might think, why have you made a video on this? And the answer to that is because the book that I've got this from, the Vector Calculus book, obviously it deals with vectors, but it doesn't really go into the theory of vector spaces. So my idea was, with this problem, to solve this problem, I was thinking, how can I go about solving this problem without directly making direct appellation to finite dimensional vector space theory and linear algebra? It might mean that I've got to kind of reinvent the wheel in certain ways, but that's the approach that I decided to take. How could I solve this problem without directly at applying vector space theory. So just so you're aware, I'm not ignorant of vector spaces. I am fully aware that this problem can be solved using vector space theory, and I've made a deliberate choice not to use vector space theory. Okay, so part of the difficulty for me was in solving this problem was actually trying to see things in a different way. When you do mathematics undergraduate level, one thing that you typically have to get your head around is the concept of a vector space. It's something that's kind of hammered into you, and you do start to think very much in those terms, and it can be quite difficult to kind of extricate yourself from those kinds of ideas. So part of the difficulty that I had in solving this problem was actually kind of tearing myself away from the idea of a vector space and going to something that's maybe a bit more elementary. Okay, so some of the first ideas that I had was to think, well, a plane can be written, there's a vector form of a plane, which is, in this case, it's going to be r dot n equals 0. So in other words, the dot product or the scalar product of the vector r, which is a vector in the plane, and n, which is a normal vector to the plane. So we might take n to be equal to a, b, c, for instance. Well, we know that a, b, and c are vectors in the plane, so we could replace r with just a, b, or c, and we get the equations a dot n is equal to 0, b dot n is equal to 0, and c dot n is equal to 0. If I wanted to write these out in more expanded form, actually calculating the dot product of a and n, well, okay, if we set a to be equal to x1, y1, z1, b is equal to x2, y2, and z2, and c, squeeze it in here, c is equal to x3, y3, z3, then I'm going to get something like, for a dot n equals 0, this is going to this is going to be equivalent to a x1 plus b y1 plus c z1 is equal to 0. This one is going to be a x2 plus b y2 plus c z2 equals 0. And then finally, a x3 plus b y3 plus c z3 is equal to 0. So I was thinking maybe I could add these together in some way, combine them in a certain way to get something like this, which is not, it's not necessarily far from, it's not too far from what we kind of need to do, but it's not a simple case of just add these together, or there's something more involved that we're going to have to do, which we'll come to in a second. But it took a while for me to, like I say, kind of get my mindset away from vector spaces and thinking, how else might I be able to approach this problem? So another thing that I kind of thought of along the way was to try to draw a diagram. Diagrams are always good things to draw, even if they don't end up being useful for that particular problem. It's still good to maybe try to get some sort of visualization of what the problem looks like. So if this is my plane, here's the origin here, and I've maybe got 3 vectors, A, B, and C. And of course, we've got vectors, for example, B minus A, which is going to be in the plane, C minus B is going to be in the plane. What else have we got? A minus C, for example. I was thinking, could I combine these in a certain way to get this? Again, it's not necessarily too far from what I do need to be doing, but it's not such a kind of straightforward process as just adding these together in or whatever. There's something a bit more involved that needs to be done. Okay, so I kind of gave up on this idea. I didn't really pursue this idea any further. These actually did come back into play further down the line for me, but I had to make a little bit of an adaptation. So I'm gonna leave these here for now, but I'm gonna need to change these in a certain way. I don't need to, but I will be changing these in a certain way just to make the problem a little bit more straightforward. Okay, so there's also it's very easy to get bogged down in technicalities from time to time. During the problem solving process, it may be helpful to be aware of certain difficulties, certain problems, certain issues that are there going on in the background, but actually for a while just kind of leave them there. So one of the issues here, one of the potential issues, and I'm not saying that this is going to be a particularly difficult problem to overcome or to factor into things ultimately. We've got to consider the possibility that A, B, and C some of them might be parallel vectors. There's nothing, the information that I've been given, there's nothing to suggest that A, B, and C are all non-parallel vectors. Okay, so it might be that all three are parallel, in which case this problem is kind of trivial again. So I don't really want to consider that possibility. I don't want to have to get bogged down with all of that. It might be the case that two of these are parallel and the third one is not parallel to the other two. Again, that kind of makes this problem trivial. It might be that some of the one or more, or possibly all three of these vectors are the zero vector. Again, we're not told this. We're just told that A, B, and C lie in the same plane through the origin. Now, I think it would be sensible maybe to assume that A, B, and C are not going to be the zero vector, but it is a possibility that maybe we've got to factor in at some point. So, in order to not really get bogged down with technicalities, I made the decision to assume that A, B, and C are all non-parallel vectors in the plane. Because I really want to get on with expressing my idea. And this is important with problem solving, because sometimes you can have an idea and it's best just to get it down on the page, get the idea expressed in symbols, and then worry about some of the finer details. Whereas if you do it the other way around, you kind of talk yourself out of actually pursuing a particular idea, which could be a really good idea. So you're just getting more and more bogged down with these special cases, these pathological cases, and your idea never really fully articulated. And what might actually be better is if you articulate your idea as in an imperfect way, and then start to think about the special cases, and you might find actually that it's relatively straightforward to factor those into your solution in some way, or that they're in many ways already accounted for. So one thing to really watch out for is really getting bogged down with detail, and this is very easy for mathematicians to get into this into this habit of really getting caught up with pedantic details. Mathematicians do maybe have a tendency towards obsessing over details, and this applies to me as much as anybody else. And sometimes it can be very difficult to just kind of allow yourself to ignore the details for a while at least. That's not to say that you ignore them completely and you pretend that the details are not important or that these special cases don't need to be considered. They do. But there's a time and a place for it, and it's not necessarily in the early stages of forming your solution to a problem. Get your idea down. If it's a good idea, then just allow it to allow yourself to express it. If it's a bad idea, then okay, you give up on it and you move on to something else. But anyway, back to this problem. So what I was thinking was, how could I go about solving the equation alpha A? In fact, I'm going to write it as alpha primed A plus beta primed B equals C. In other words, since we're assuming that A, B, and C are not parallel vectors, how can I find values, constants, scalars, alpha primed and beta primed, such that alpha primed A plus beta primed B is going to be equal to C? And I'm using alpha primed and beta primed because although I'm going to be looking to find specific values for these, and I could use these as my alpha and beta up here. It's just I'm not going to. I'm going to change the values slightly. So there will be a relationship between alpha primed and alpha and beta primed and beta. But then I'm not going to be using alpha primed in place of alpha. Okay, so I thought, well, rather than trying to match up all three components of the vectors straight away, maybe it would be easier for me, at least just to get an idea, maybe, going forward. Maybe let me just see what happens when I try to match up two of the components. Okay, so I know that A and B are not parallel. That's the assumption that I've made. A and B are not parallel. So that means that it's possible for me to choose two components, either both of the x and the y components of each vector, the x and the z components of each vector, or the y and the z components of each vector, such that, let's say, I'm going to use x and y just as an example, such that x1 times y2 minus x2 times y1 is not equal to 0. If this does happen to be equal to 0, then maybe I have a look at x1 times z2 minus x2 times z1, check whether that equals 0. If that equals 0, then I choose y1 z2 minus y2 z1, and that will be non-zero. So one of these quantities must be non-zero. It might be that at least one of them. It might be two of them, it might be all three. But I'm going to choose one of these, just one of these, which is non-zero. And let's just assume, for sake of argument, that it's this one, that the x and y components are such that x1 times y2 minus x2 times y1 is not equal to 0. And you'll see why this is going to be important in a second. So then what I do is I think in terms of simultaneous equations. So alpha primed A plus beta primed B, this is going to give me alpha primed x1 alpha primed plus x2 beta primed is going to be equal to x3. And y1 alpha primed plus y2 beta primed is going to be equal to y3. Okay, so remember that the x's, the y's, and the z, they're the constants here. They're not the unknowns. The unknowns here are alpha primed and beta primed. So I could write this as a matrix problem if I wanted to, and it's going to look like this: x1, x2, y1, y2, alpha primed, beta primed is equal to x3, y3. So for those of you that know about 2x2 square matrices, you will understand now why I've chosen this condition, because this is the determinant of this matrix, and what I'm wanting to do is effectively find the inverse of this matrix, which is only possible for me to do provided that this condition applies. If this was equal to 0, this matrix would not be invertible, which would not allow me to do what I'm about to do. So again, if this was equal to 0, then I would just choose another two components. I don't have to write this as a matrix problem. I could use these simultaneous equations. So if you've done, for example, GCSE Maths, higher maths, certainly if you've done A-level maths, even if you've not come across matrices and expressing simultaneous equations in a matrix form, you could still solve these using the standard techniques, the typical techniques that you've been shown in the classroom solving simultaneous equations. Just remember though that the x's and the y's here are our constants. It's the alpha prime and the beta prime that are the unknowns. So if I find the inverse of this matrix, then I get this, that alpha prime beta prime is going to be equal to x1, x2, y1, y2 inverse times x3, y3. Okay, coffee time. So what that does now is it gives me some values for alpha primed and beta prime. So what happens is I get alpha primed is equal to, and I'm going to have to refer to my notes for this, is going to be y2 x3 minus x2 y3 over x1 y2 minus x2 y1. So we can see again why we need this condition. So even if we don't think in terms of matrices, if we did solve just using the simultaneous equations here, we'd still arrive at this value for alpha prime, but we would still require x1 y2 minus x2 y1 to be non-zero for this expression to make any sense. Division by zero, bit of a no-no. Okay, so beta primed is equal to x1 y3 minus y1 x3 over x1 y2 minus x2 y1. Okay, and it's not difficult to verify that these values do solve these simultaneous equations. If you're in any doubt, go ahead and check. They do work. I've tried them. Okay, so then I was thinking, this is all well and good. This matches up the first two components. Okay, so in this equation, I've not solved this equation as such. I've partially solved this in the sense that I've got the first two components all to match up. I found constants that I need to multiply the first two components by here to get the first two components here. So that's great. However, what about that third component? Okay, so I need to make sure that the third component matches up as well. Is it possible for me to just use these constants that I found here, or do I need to modify these in some way to account for that third component? Now, if this had been maybe while I was doing my undergraduate studies, I would probably been a little bit quicker off the mark here and realised that yes, I can use these in a certain way. I did come to that conclusion eventually. It just took me a little bit longer than maybe it would have done, say, 15 or more years ago. Okay, so let's get rid of this. We don't need this anymore. But one good thing about problem solving is that even if you can't remember something off the top of your head, a certain fact, a certain formula or something like that, if you understand the logic of mathematics, you understand that problem solving is a way of gradually revealing the relationships and the properties of certain things that you're working with. So even if you can't remember, I couldn't necessarily remember whether these would suffice for the third components to match up as well. I couldn't remember that off the top of my head. It didn't matter. It just meant that I had to spend a little bit more time just rethinking things through and using the logic to tell me something which maybe I knew a long time ago, but which I've forgotten now. So bear in mind that if you forget something in mathematics, if you're ready to, if you understand the logic, you understand the concepts that you're working with reasonably thoroughly, then that forgotten fact might be something that you can either work around, or you can recover that fact. It's not like I often compare it to a pub quiz. It's like, do you know the currency of, I don't know, Venezuela? It's either yes or no. There's no logical process. Either you've been told this, or you haven't been told this, or you've read it, or you haven't read it, or whatever. But there's no logical process that you could go through to recover that bit of information. Maybe you knew it at one time, but maybe you've forgotten it. If you've forgotten it, you've forgotten it. And if you can't just remember it, then tough. But there's no logical process that you can go through. But people often see mathematics as working in the same way. You forget something, well, I can't do anything then. You've forgotten the quadratic formula for solving quadratic equations. Oh, well, I can't solve this quadratic equation. Well, no, there's other things that you can do. You can either work around that problem, or you can rederive the formula. And sometimes it's easier to remember how a formula is derived rather than trying to remember the formula itself in some cases. So bear that in mind when it comes to problem solving, that just because you can't remember something doesn't mean that all is lost. Okay, so coming back to this then, let's get rid of that as well. We're not going to need that now. Okay, so at this point, I realized that, for example, if we take this here, ax3 plus by3 plus cz3, that means that I can write z3 in terms of x3 and y3. Now, if I just use this, then I'm going to get something that's going to be quite clumsy. I'm going to get something like z3 equals minus a over, assuming that c is not going to be equal to 0, by the way, minus a over c x3 minus b over c y3. And I thought this seems a bit unnecessarily complicated. So what I did instead is I changed this a little bit. And I said, rather than having a, b, and c here, I'm going to have minus a, minus b, and 1 as my normal vector. Okay, so that means then that I can write, for example, that z3 is going to be equal to ax3 plus by3. And I can do similar things for these as well. And write these in a similar form. So in other words, I get z2 is equal to ax2 plus by2, and z1 is equal to ax1 plus by1. It's not essential that I do this, but it's something that's that I can do if I choose to do it. And also, yes, there is a technical issue here. What if any normal vector to our plane has a 0 component in the z in the z position here? Well, in that case, then the calculation could be redone from a different perspective, choosing one of these components has to be non-zero. Okay, so you can just redo the calculation. Again, I don't want to get bogged down with fine technicalities. I really just want to communicate the process, the thought processes that I went through in order to arrive at my solution, which is not going to be perfect. The solution is not going to be perfect because it's not going to take into consideration all of these fine technical details. And I don't care about that. I care about how I arrived at my solution. And once I've got my rough solution, then potentially I could go back, and I should go back and refine it and look and weed out all of these problems, these certain issues that might arise. So we're going to overlook certain issues for the time being. Okay, so that being said, let's have a look at, let's go back to this equation then. So if I use the values of alpha prime and beta prime that I've already found, then if I use the Z1 and Z2 that I've got from here, then I will get that alpha primed Z1 plus beta primed Z2 is going to be equal to alpha primed A x1 plus alpha primed B y1 plus beta primed A x2 plus beta primed B y2. And careful observation reveals that this is equal to, I've got to get this right, A times alpha primed x1 plus beta primed x2 plus B times alpha primed y1 plus beta primed y2. But I know, because of how I found these in the simultaneous equations that I used to find these, I know that alpha primed x1 plus beta primed x2 is equal to x3. And I know that alpha primed y1 plus beta primed y2 is equal to y3. So this is, therefore is equal to A x3 plus B y3, which is equal to Z3. Aha, okay. So using these constants, I find that not only do the x and y components match up, but the z components also match up in this equation. So therefore, the alpha prime and beta primes that I found here suffice to solve this equation for, it matches up each of the components, not just the first two components, but all three components. So that's a big bonus. Okay, so in other words, get rid of this. I can take the constants alpha primed, beta primed, and -1 as the constants that I'm looking for, because in that case, if I just rearrange this, I get alpha primed A plus beta primed B minus C is equal to 0. But I'm not going to do that. What I'm going to do is I'm going to multiply through by x1, y2 minus x2, y1, which gives me then that alpha is going to be equal to y2, x3 minus x2, y3. Beta is going to be equal to x1, y3 minus y1, x3. And gamma is going to be equal to minus the negative of this, minus x1, y2 minus x2, y1, or x2, y1 minus x1, y2, whichever you prefer. So these values of alpha, beta, gamma suffice to solve this equation, provided that A, B, and C are equal to these particular vectors, on the assumptions that A, B, and C are not parallel vectors, and the various other assumptions that I've kind of built in. But if any of those assumptions fail, it's, for example, if x1, y1, x2, y2 are such that x1, y2 minus x2, y1 is equal to 0, no problem. Just choose either the x and z components or the y and z components. If it happens that the z component here is equal to 0 in the normal vector, okay, just choose one of the other components. You might have to kind of backtrack a little bit, redo some of your calculations, but it's not a problem. The calculation can be redone. So I'm going to leave my solution to that here. I'm happy with that solution as far as it goes. I've expressed the main idea of my solution to the problem. Then it just remains to really consider the technical details, iron those out, and produce a satisfactory final solution.